Hello, students. So I will talk about limits of functions. What kind of functions we are considering here is that we are considering real functions. I mean that any function f that we will consider, it will have a domain, some domain E, and its range will be in set of real numbers. But this domain E, which is domain of this function f, in short, we will denote sometime it by domain F. This will also be a some subset of real numbers. Since first we have to begin with the limits, for the limits, we will consider this domain to be some interval or some punctured interval means if at a certain point we want to compute the limit, we will consider an interval not containing that point where the function is not defined. But let me begin with this definition of a limit of a function. So let us take a point. It's a real number, point in R, where this R denotes the set of real numbers, and I be an open interval, be an open interval which contains the point A, which contains the point A, and that f be a real function, be a real function defined here except at the point A. That is what we can say this thing that in this case, what I'm taking, this function f is defined on the interval I minus A. It can be defined on A as well, but we possibly we don't have this requirement here that f needs to be definitely defined on A. There is no requirement for to check whether a limit of a function exists at a point, and to check where the limit exists, a function need not be defined there. You don't have that requirement there. So then we say that, all right, instead of f of x converges to some number L. I will take this to be a finite real number L as x approaches A if and only if and only if for every positive number epsilon greater than 0, there exists a positive number delta bigger than 0 such that the value of the function at x minus L, its absolute value, which is geometrically the distance of the value fx from L, is less than epsilon whenever the distance of point x from A is less than delta. But in the definition, we have considered a function where this function is possibly not defined at the point A. Therefore, we have to avoid the point A. And so that's why we have to take this absolute value to be strictly positive. because this is the only way how to avoid this value. Otherwise, if you take x minus a, x equal to a, then you can take this absolute value to be 0 also. So you have this situation that uh, the value of the function comes closer to the point value L as the value of x comes closer to point A. In notations, we denote it as limit x approaches to A, f of x equals to L, or we might have this notation as well, f of x converges to L as x converges or approaches to A. This will be our standard notation to denote this limit, and then this point, this value L, this L will be known as, we can call it as limit of function f at A, if and when it exists. Let us consider the simplest example to understand what it is saying. We have this simplest example first. Let me consider the function f of x, the linear function mx plus b, and suppose your m and b are finite real numbers and they are constants. Then here I will show this thing that the limit of this function exists at every point on R, and you see this function is defined everywhere on R. Its limit exists on R, and indeed we will show this thing that uh, the limit of this function at any point is the value of the function at that point. This is very rare to happen with all the functions, as we will see. Not this doesn't happen with every function, but yeah, this is a special function, and this is a class. This class of functions. This class of linear functions is amongst one functions, very special type of functions. What you call them as continuous functions, where this limit of a function at a particular point is nothing but the value of the function at that point. But okay, let's focus first on the calculating the limit of this function. So first, suppose a is any real number, and then we have to compute its limit. Now, if m is a constant, m can be 0 as well. If m is equal to 0, then your function f of x is equal to b, and then you see this f of x minus f of a. In this case, the function becomes constant. It will be b minus b. It is 0, and this 0 is less than epsilon for any epsilon greater than 0. So here you don't need delta. Here it will work for any delta, for any choice of delta satisfying 0 less than x minus a less than delta. This is indeed redundant to say that you require here delta. This is trivial here. We didn't have anything to prove indeed here in this case when your m is 0. So we can say this thing, and then in case of m is equal to 0, then the limit exists, whatever it is in the claim. It exists trivially. So we suppose now, and we consider the case where m is non-zero. Let us consider that m is non-zero. Suppose that m is not equal to 0. Then what happens? Then we have to consider this choice of delta. What should be the delta for given epsilon greater than 0? We have to choose some delta. Choose delta equals to something, whatever it is. Let me write it later. because that case will come to you from the computation. So note, I have to choose delta in such a way that when I compute f of x minus f of a, which is actually m of x plus b minus m of x minus b, which comes out to be m of x uh, m of a minus m of a. If you use the multiplicative property of this absolute value, then it is absolute value of m times absolute value of x minus a. So now from here we can guess what should be our choice of delta. Look, I want this and this f of x minus f of a absolute value to be less than epsilon, and this absolute value will be less than epsilon when this absolute value of m times the absolute value of x minus a is less than epsilon. And at the same time, we have to consider this absolute value of x minus a to be less than delta. And if it comes out to be less than delta, it will be absolute value of m times delta. And I want it to be epsilon. And this is possible to have this to be epsilon when if we choose delta to be what? We can choose delta to be epsilon upon absolute value of m. So this is the choice of delta. And if and clearly, of course, whenever your number epsilon is positive and you're considering this case where m is non-zero, so its absolute value is positive, then this is a positive number. And you see this number depends upon epsilon. Indeed, in the definition of the limit, we need to be careful that this epsilon will depend on epsilon, and it will also depend upon the point where you want to consider the limit of a function. For a particular choice of function, if you look at 10, 20 or a big class of functions, then this delta will depend upon the function as well, and the interval also. And so here it follows that since epsilon was arbitrary, you found out a delta, which is a definite number depending upon epsilon, for which you have this f of x minus f of a less than epsilon whenever your distance of the point x from a is less than delta. Hence, we can see this thing that by definition of the limit, it follows that the limit of this function exists at any point, and the value of the limit is nothing but the value of the function at that particular point. So this is the example, simplest example of a function where the limit of the function exists. Let us consider now an example where the limit of the function doesn't exist. So first recall this thing. And by definition of the limit, we see this thing that mm, let me go to the definition. Definition says that you have an interval. You have an interval uh, containing the point at which to find out the interval of the function, so which contains a, and this is an open interval. So what open interval means? That means to check out the definition of a limit of a function at a particular point, whether that limit exists there or not, you must have an open interval containing that point. And you see, once this a is contained in an open interval, then definitely this a is not one of the endpoint of that interval. That means to the left as well as to the right of this point a on the real axis, on the real line, there is a portion of this interval. And your function f is defined everywhere on this interval I, where the except possibly on a. So that but if this interval is spread in such a way that some part that a is in it, and some part of this interval is to the left of a, and some part of this interval is to the right of a. Or in short, what I want to say is that whenever you want to check out the limit of a function at a point, then that function needs to be defined immediate to the left and immediate to the right of that point. If you have a function which is not defined on either side of that point, then obviously the function will not have a limit at that point. And for this, you consider this function f of x square root of x, and it is defined on 0. At 0, it has a value 0, and you see that since for x less than 0, f of x remains undefined, is not defined. So what we can say? We can say that we cannot talk about the limit of a function at, so it doesn't exist indeed. It doesn't exist at 0 because the function to the left of 0 is not defined. So this is an example of a function where the limit doesn't exist at that particular. You can check at other points the limit of this function exists, but my motive here was to tell you an example where the limit doesn't exist. Moving on, let us consider a function where you require bit of work to compute the limit of a function. So I'm considering this function, which is a polynomial. It's a quadratic polynomial, and I have to use the definition of the limit to prove this thing, that the limit show that limit of x tending to 1 of this function fx is -1. I have to show this thing. What is -1? -1 here is actually the value of the function at 1. This is actually f of 1. And indeed later on we will see that this happens in case of not only this polynomial, it happens in case of every polynomial. In case of every polynomial, keep this in mind. Keep in mind, we will come to this later on once we develop more tools to handle this, that for any polynomial, p of x and any point in R, this thing happens. Limit x tends to a p of x is exactly the value of the function at that polynomial at that point. So polynomials satisfy this kind of behavior that was exhibited in this example 1. So the functions, the class of functions exhibiting this kind of behavior is much larger than the class of linear functions, because polynomials will be there in this class. But okay, this is just a digression. So let us work on this thing. But our approach here is to just to use the definition only epsilon and delta to compute the limit. So what we want to do here, we just begin with some positive number epsilon. Let's take some positive epsilon number, and we have been told to establish that the limit of this function polynomial at 1 is -1. So let us put L to be -1. And now let us try to guess something from f of x minus L. This is x square plus x minus 3 minus plus 1. It will be 1. And so it comes out to be x square plus x minus 2. And if you factor it out, it is x minus 1 into x plus 2. And hence, because we want the distance of f of x from L, or it is nothing but it is the absolute value of f of x minus L, it comes out to be x minus 1 mod of x plus 2. So here we will again have to look at things because we have to choose a delta. We have to find a delta such that this part becomes less than delta. We have to take this to be less than delta. We have to choose less than delta. And then there is this extra part that I'm putting this in this circle. We want to choose delta in such a way that this minus 1 becomes less than delta, absolute value of it. And at the same time, this absolute value of x plus 2 remains bounded by some quantity m. So there is a choice. If we choose 0 less than delta less than equal to 1, see what happens then, that we can see this thing that x minus 1 less than delta implies 1 minus delta less x less than 1 plus delta. But your choice of delta also gives you this thing, because delta is maximum value 1 and minimum is it's less than 0. So this is greater than 0, less than 2. So if you have a choice of delta lying between 0 and 1, which can at most go to up to 1, in that case the x will be a point which will lie between 0 and 2. And if it lies between 0 and 2, then we can have more absolute value of x plus 2, because we want it to be bounded by some quantity. It will be less than or equal to mod of x. I'm using the triangle inequality 2, and this is less than or equal to 4, because mod of x is less than 2, 4. So now we have this thing surety, that if we take restrict our choice of delta to be between 0 and 1, then we can bound this encircled quantity, which is mod of x plus absolute value of x plus 2 by 4. And if this comes out to be 4, I want this something 4 times delta to be less than epsilon. So let us choose this in this way. So choose delta to be minimum of 1, and we can choose it to be epsilon by 4. Hence, for 0 less than x minus 1 less than delta, we have, I will directly copy this expression here. Let me put this whole expression as a star. From star, what will happen? We have absolute value of f of x minus L, which is absolute value of x minus 1 of x plus 2. And this thing is less than or equal to, because we have chosen delta to be, we have to be kept in mind that delta has to be less than epsilon by 4, and it has to be less than 1 also. So that's why we have to take it minimum of 1 and epsilon by 4. So it is then delta, then in that case x plus 2 absolute value less than 4, then delta times 4, because delta is then epsilon by 4. Here we have this less than, just let me make a correction. It has to be, because you have to take absolute value of x minus 1 less than delta, so it will be strict inequality here. So this becomes less than by then delta is from the definition of delta is less than epsilon by 4 into 4 is 4 will cancel, is what you form, that the distance of x from L is less than epsilon whenever the distance of x minus 1 is less than delta and greater than 0. We are not considering x to be equal to 1 as per the definition of a limit. And that simply is nothing but it is the of the function as mentioned to be minus 1. So this limit exists. So these are sufficient example. We give an example where the limit exists. We give another example calculating limit at a particular point, and at the second example, we give an example where the limit of a function doesn't exist at certain point. Now, the main talk of this lecture is to link the existence of limits with the convergence of sequences. And that will be much helpful to understand the limits. And for that, the result that I'm going to tell you here is that we call it as a sequential characterization of limits. So what it says, our requirement is to have an interval where the function is defined except possibly at the point where the limit is to be calculated. So let us put that requirement first. Let us take a to be a point at which we want to compute the limit, and I be an interval containing a be an open interval containing a, and that f be a real function defined everywhere except possibly on a. Then the limit of this function at the point x equals to a exists and is equal to L if and only if the sequence f of xn converges to L as n tends to infinity for every sequence xn in I, but no term of this sequence has to be equal to a. That's why we are taking xn in I minus a, so that xn is not equal to a, such that this sequence converges to a. So that means any sequence which converges to a, then the corresponding image sequence under f must converge to L. If it happens, then the limit of the function will exist and converge also. And this is the sequential criteria. And we will see with the help of an example how this is useful. And there are many other results of the existence of a limit which will be proved by using this sequential criterion, which will very helpfully shorten our proofs if we use this result to establish many other facts of the limits of a functions. Look at the proof. Uh, for proof, first, suppose that limit of this function exists at point a, and suppose the value of this limit is L. Okay, and now let us take a sequence xn in I minus a such that xn converges to a. Now our target is to show that the image sequence f of xn converges to L as n tends approaches to infinity. So we have to prove this thing. Now to do this thing, usually how do you prove that whether a given sequence is convergent or not? You just begin with some positive epsilon, and once you have given epsilon, you just go back to the definition of a limit here and use that epsilon here and find out some delta. So then there exists some positive number delta greater than 0 such that what will happen whenever 0 less than x minus a is less than delta, it will imply that the distance of f of x from L will be less than epsilon. Okay, Let us call it as star. But at the same time, because now you have found a positive number delta, and now you use the definition of the convergence of the given sequence xn converging to A. And by the convergence of the sequence, there is some natural number. There is a natural number n such that whenever small n is bigger than or equal to n, it will imply, because the sequence is convergent, it will imply xn minus 8 absolute value is less than delta. Now look at this thing. Star inequality in star. The second inequality in star holds whenever the point is in a delta neighborhood of A, or in a delta neighborhood means the distance of point from A is less than delta. In double star, each term after n, for each term after n, the distance from A is less than delta. So we can apply this star to equation double star, and then we get, so I can say from star and double star, we have for the choice n greater than or equal to n, you will have f of xn minus L. This becomes less than epsilon when xn, distance of xn from A is less than delta, and this distance becomes less than delta when you choose n to be greater than or equal to n, capital N. So this will be less than epsilon. And what is this thing? This thing, by definition of a convergence of a sequence, is a convergence of the sequence fxn converging to L as n tends to infinity. So this proves the direct part of the sequential characterization of limit of functions. Let us look at now the converse part. Conversely, what we need, conversely, suppose that the hypothesis is that fxn converges to L as n tends to infinity for every sequence xn converging to A, but this sequence xn needs to be in I and no term has to be equal to A. Then we have to show that the limit of the function at A exists and its value is L. Suppose not. Suppose limit of this function at does not exist. So what happens then? By definition of the limit, that means for some choice of epsilon, your definition part of the limit will not hold. That means there is some positive number, let that positive number be epsilon, such that for this choice of epsilon naught, the implication of the definition, what implication? This one. Let me change this thing such that the implication, this one, definition part says that f of x minus L should be less than epsilon for 0 less than x minus, here it is epsilon naught, we are considering delta less, sorry, this is A, this is less than delta. So this thing will not happen, this thing will not hold. So this does not hold. What is delta here? This will not hold for any delta, whatever delta you choose, for this choice of epsilon naught. This will not hold for anything if you suppose that the limit of the function doesn't exist. What it means, in particular, if it doesn't hold, it means that for each choice of delta, and let me take the choice to be more specific, for each delta equals to 1, there will be a point for which this inequality fx minus L will not be less than epsilon, it will be greater than or equal to epsilon. So there is some point xn in I different from A such that f of xn minus A will be greater than or equal to epsilon, and at the same time the distance of xn minus A from xn, distance of xn from A will be less than delta. Here delta is n for each n. Now look at this inequality. If you now you found a sequence, xn, and this sequence satisfies this inequality. And if you remember the comparison theorem for sequences, then comparison theorem clearly specifies this thing, because the left hand sequence goes to 0, right hand sequence goes to 0. So xn minus A will go to 0. That is to say that xn converges to A. So comparison theorem will say, or you can also talk about instead of comparison theorem, we can go to squeeze theorem. You can squeeze theorem because the right bound goes to 0, left is a 0, so the middle one will also converge to 0, and middle one is absolute value of xn minus A goes to 0. That is equivalent to say that xn converges to A. So you have that sequence xn has a limit A. You can write in sequence convergence notation. And so your sequence xn is converging to A, and then you have this standing hypothesis that the image sequence, this implies that f of xn will converge to L as n tends to infinity. F of xn is converging to L. That means in particular, f of xn is close to L for large values of n, or in particular, f of xn minus L will be less than epsilon naught for large values of n. But this cannot happen because you look at this this part of this inequality here. Let me highlight it. This part says that whatever value of n you take, then the absolute value of fxn minus A is greater than or equal to epsilon naught. And so this thing goes in contradiction with this. So this is nothing but this is a contradiction. And this contradiction is a consequence of what we have as taken as an assumption that the limit of the function doesn't exist. Therefore, we were wrong. Hence, the limit of this function exists at x equals to A, and its limit is 1. So this is a very important result which characterizes or which equivalences your definition of a limit to the convergence of a sequence. For the sake of applicability, consider this example. Let me consider this function fx. I'm defining it to be sine 1 by x for x not equal to 0, and this is 0, x equal to 0. So for x not equal to 0, it is understood it is a well-defined function. It doesn't have any problem. At 0, we seem to have problem, and we will see that its limit at 0 doesn't exist. If you look at the behavior of this function, if you can plot the graph, and the more you will come closer to 0, initially it will behave the way sine function behaves, but you come closer and closer to 0 because your sine function is 2 pi periodic function. It is a periodic function, and once x comes closer and closer to 0, 1 by x becomes larger and larger, and so then this vibration of this function becomes too fast. It becomes when x comes close to 0, it attains its extremes too fast, because you look at this function, look at this number an equals to 2 upon 4n plus 1 pi, and you look at this function bn, not function, these are the numbers, and so I'm considering these sequences 3 pi. So at an, the value of the function is going to be 1, and at bn the value of the function is going to be minus 1. At f of an, value takes the function 1, and f of bn, it takes minus 1. You can check out where does x sine of x takes value 1, sine of x takes value at odd multiples of pi by 2, and then minus 1 you can take, you can consider 4n plus 3 multiples of 90 degree, it will take minus 1. Here 1 by x, that's why we have 2 upon 4n plus 3 pi. So, but an converges to 0, bn also converges to 0. So you have two different sequences. Both the sequences are converging to 0. But corresponding image sequences are constant sequences. One is a constant sequence 1, another is the constant sequence minus 1. So first one converges to 1 because it's a constant sequence. The second one will converge to minus 1 as n tends to infinity in both the situations. So what situation you have here in this case? You have two sequences. They are converging to 0, but the corresponding image sequences are having different limits. They are not having the same limits. If this function had a limit at 0, then according to the sequential characterization of the limits, for these two different sequences converging to 0, the corresponding image sequences must have the same limit. But here the limit is not same, therefore limit of this function doesn't exist at 0. Does not exist. So I will stop here.